Alright, hey guys, I'm here today to show you about how some infinities can be larger than other infinities, and moreover, how the set of all real numbers is uncountably infinite, whereas the set of all integers is actually countably infinite. So we have two ways of having infinities. One's countably infinite, which would be something like the set of integers, like 1, 2, 3, 4, 5. So we call it countably infinite if for each element of the set, you could give one set of the set of integers, and that's by definition. So for this, it would be very simple. You could just write 1, 2, 3, 4, 5, and you can see that it will have an equal number of elements as the set of integers. Then you can also do this including negative numbers as well. So if you start 0 or -1, 1, -2, 2, -3, 3. You can also map them each to a number 1, 2, 3, 4, 5, 6, 7, etc. So this is actually considered countably infinite, the number of negative numbers plus the positive numbers plus 0, because even though this increases what may seem as double the rate, you can still provide an integer to map it to. And this is what you call being bijective, because there's two things involved. One is being onto, and one is called one-to-one. So for this, you can see, I'll actually define one-to-one right now. Y equals x plus 2 would be a one-to-one function, because for each x value, let's say x is equal to 1, then you can have y is equal to 3. If x is equal to 2, y is equal to 4. So each x has a separate y. If you continue, you'd notice that it's impossible for two x's to have the same y. And onto simply means that each x value has an element in y, which is quite obvious because there's no impossible value when you're just adding 2 to x. So now let me explain how the set of real numbers is uncountably infinite, which means it's actually larger than countably infinite. So essentially what is done is proof by contradiction. So firstly, you assume that the set of all real numbers is actually countable. So I'm going to write here 0.1, 2, 3, 5, 6, 8, 9, like etc. And it continues. Then I'll write another one, 0.2, 3, 6, 4, 8, etc. I'm just going to write random numbers or another digit there. 1, 4, 2, 3, 7, 6, 4. These are just off the top of my head. And I try to map an integer to each of these. So 1, 2, 3. And I assume that this is actually going to work out and that it's actually countably infinite. So let me just add another number to this set. So I assume that I can actually do this, and I can have all the integers map to each number. So now I'm assuming that it's countably infinite. Now the surprise here is that I can actually, even though I assumed that I created every possible combination of real numbers, this list goes on continuously and this list goes on continuously this way, I can prove that there's an extra possible element to be added. And this is quite simple. It's called the diagonalization theory. So essentially, I can take this first element of I and first element of j and create a number that does not have this digit. Because it's a 1 here, I could write a number with like a 2 here, right? And now I know for sure that it's definitely not one of these numbers. So it's a new number. Then for this second one, what I simply do is I ensure that the second digit is not equal to this. So I'd write 4, for example. And I keep going down each of these elements diagonally, and assuming that it's countably infinite, I just prove that I can add at least one number, obviously many more, but at least one number to this countably infinite set, thus being greater than countably infinite, and thus this set is actually uncountably infinite, which is the proof of being uncountably infinite today. Thank you very much for your time.